Now, recall that a few lines above I stated a solution of a system must suffice all equations in the system. Now, these solutions can be found in a few ways, and we're going to start delving into the elimination and substitution methods that we've probably learned in Algebra 2, and if not, we'll review them, introduce them, sorry. And now, in the case of two variables, there are, not only in two variables, in multiple variables. So in a system of linear equations, there's a possibility, so in a system of linear equations, there are three types of solutions that can be found through this process. So the first type, but they're categorized in two categories. They're categorized as either that's the E, consistent or inconsistent. Now, the difference between consistent and inconsistent systems are a consistent system has at least one solution, meaning one solution is okay, two solutions are okay, infinitely many solutions are okay, and the opposite for inconsistent. Inconsistent has no solutions. Now, how do we go about solving these types of systems? So, in the case of a two-variable system, so let me change to this. How to solve systems. And again, this is of linear equations. And in this case, I'm going to do two variables. And that's my abbreviation for variables. So for two systems, we have a few methods. So the one method that we've solved that we like is elimination method. So and that method consists of adding or subtracting onto this is example 5, correct? Yep, example 5. This elimination method is where you multiply onto one equation, add it to the other, and use that new equation to solve for the system. So in example 5, we're going to have x plus y equals 3 and x minus y equals -1. So when I would teach this, I always like to put this in two steps. So step 1, well, the purpose is solve for one variable. So you need to have same coefficient, opposite signs for x or y. Step 2, add the equations. Step 3, you might have to simplify them, divide or something like that. Simplify. And then what they call back substitute. All right, well, let's try this out. So step one says you need to have the same coefficient, opposite signs for either x or y. So my x's, put a box around, let me highlight it. Oh, that's too big. 1 second, all right. So my x's, notice, they're already the same coefficient, awesome, but not the different signs. Let's look at my y's. My y's in yellow are same coefficient, opposite sign. So perfect. My step one is already done for. Now step two, we need to add the equation. So let's add these. So step two, add equations. So now if I add x plus x, that's going to give me 2x. The y minus y, that'll give me 0. And then the 3 minus 1 will give me 2. Step 3, simplify. Oh, I should probably put solve. So in this case, I'm going to simplify by dividing by 2. So step 3. Oh, divided by 2. My bad. So my x is going to be 1. Now step 4, back substitute, meaning plug this x back into either equation, either the first one or the second one. So if x equals 1, then 1 plus y equals 3, and y equals, subtract 1 on both sides, 2. So my solution to the system should be 1, 2. But again, it needs to check, so need to suffice for both. And if you did the process right, this should always be the case, but it's always good to double check, especially on exams. So if I plug in 1 plus 2, does that equal 3? Yep. If I plug in 1 minus 2, does that equal negative 1? Yep. So my solution works. So this is called elimination. Again, you're adding, multiplying onto the equations and then reusing those. Now, a second method. Let's see. A second method would be substitution, but we're not going to be using substitution in this case. We're going to be using this elimination method. So now let's move on to example 6. And we're still solving for our equation. So example 6. And I want you to solve for the system x plus y and this is the y right here, not a g. I actually guess I should erase it. Alright, now we would go about this by using the 4 steps above here in this rectangle. Now, notice the first equation has coefficients of 1, so in order to make it into coefficients of 2 with opposite signs, so step 1, we need to multiply first equation by negative 2. So if I do that to negative 2, then I'll have negative 2x minus 2y equals negative 8. And my second equation stays the same, 2x plus 2y equals 8. Now notice the first equation changed because I manipulated that first equation. And this is remain the same. These two equations remain equivalent because notice whatever I did to one side, I did to the other. And you know, equality works that way. If you have, it's still the same if you do it to both sides. Now step 2 would be to add these. But if I add these, I'm going to get 0 plus 0 equals 0, which is a true statement And step 3, I can't do anything. Step 4, I can't do anything. So step 3 to step 4, we're already done. Well, what does this mean? This is true no matter what numbers I plug in. Meaning, this has infinitely many solutions. So, infinitely many solutions. Well, how? Why does that mean infinitely many solutions? If you notice the second equation, let me do it in pink. Note, this second equation is the same or equivalent to 2 times x plus y, 2 times, which is equal to 2 times 4. If I divide both sides by 2, I'll get x plus y equals 4, which is technically the same equation as the first one. Now, what does that mean? Well, on the number line, if you think about plotting this, this is my, if I solve for this, y equals negative x plus 4, so my y-intercept is 4, and my slope is down 1 over 1, down 1 over 1, and so on. There you go. Now, that's x plus y equals 4. If I multiply it by 2, I'm going to do that in yellow. 2x plus 2y equals 8. Well, that's the same thing, except it's just been elongated, or it's longer now. It got stretched out by a factor of 2. So see, the lines are technically the same over the overlap, so in this case, you have infinitely many solutions. Now take note, when does this happen? Infinitely many solutions happens when it's a scaling factor, meaning I scaled this equation by 2, by multiplying by 2. And essentially they're the same line. Alright, now let's go on to a different type of example. Now in example 7, again, same instructions, solve for the system. X plus y equals 3 and x plus y equals 1. Let's try our elimination method. Well, actually, let's try the other method that we're not going to use. So substitution. Well, that one can be categorized in steps as well. Step 1, solve for one variable. Step 2, substitute into the other equation that you didn't solve for. Step 3, solve for the variable, the remaining variable. And then step 4, back substitute. And I'm going to abbreviate back substitute by back subs. Alright, so step 1. Let me solve for the variable, the denominator. So solving for y of x plus y equals 1, subtract x, I have y equals 1 minus x. Step 1. Step 2, substitute into the other equation. So I'm going to substitute y equals 1 minus x into x plus y, which is now 1 minus x, equals 3. Step 3, solve for the remaining variable. So now I have of 3. X plus 1 minus x equals 3. X and minus x go away, so 1 equals 3. But we know this is a false statement. Thus, this has no solutions. Now, if we represent this on a graph, if we have 1, 2, 3, 4, 1, 2, 3, 4, and sorry, my lines will not be perfect. So the first one is y equals 1 minus x, so coefficient y-intercept of 1, down 1 over 1, down 1 over 1, and so on and so on. Roughly fitting right there. The other line, if I subtract x on both sides, that's going to be y equals 3 minus x. So 1, 2, 3 over 1, oops, down 1 over 1, and so on. Something like that. Now, notice, if these were perfectly aligned, this would be the case when they are parallel lines. So this will always be the case. There's no solution when there are parallel lines because the lines will never intersect. And I didn't mention it in the first elimination method, the example 5. But when there's this one solution, this is the case when the lines overlap. So if I come back up here to example 5 and I plot out the graph, which I'm doing right now, then I'll have the first equation, subtract x, that'll give me y equals 3 minus x, 1, 2, 3, down 1 over 1, down 1 over 1, and so on. Something like that. My other equation will be subtract x divided by y equals x plus 1, y-intercept of 1, up 1 over 1, up 1 over 1. Which, if you notice, the intersection point is my solution, 1, 2. So you have one solution when your lines intersect, infinitely many solutions when they're the same line or they're scaling factors at same lines or scaled factors, which means the same thing. And like example 7 is no solutions when there's parallel lines.